All right, welcome everybody to my talk, Dissecting QNX, Analyzing and Breaking Exploit Mitigations and PRNGs on QNX 6 and 7. So who are we, or who am I, rather, in this case? My name is Jos Wetzels, and I'm an independent security researcher with Midnight Blue, where I mainly focus on embedded system security. I previously worked as a security researcher with the University of Twente in the Netherlands, where I focused on critical infrastructure protection. And most of this work was done as part of my Masters of Science thesis at the Eindhoven University of Technology in the Netherlands. My colleague who cannot be here today is Ali Abbasi. He's a PhD candidate at the Eindhoven University of Technology and a visiting researcher at the Ruhr University of Bochum. And he mainly focuses on ICS and embedded binary security as well. So I'll start off with a little roadmap. I'm going to start with an introduction to the QNX operating system, then move on to the operating system and security architecture outlines, before discussing the QNX PRNGs and exploit mitigations and finishing off with some final remarks. So what is QNX? QNX is a Unix-like POSIX-compliant embedded real-time operating system, initially released in 1982 and later acquired by BlackBerry. It's a closed-source operating system and it's proprietary. QNX versions up to and including 6.6, which was released in March of 2014, are 32-bit operating systems, but the newly released QNX 7 is a 64-bit operating system. It's most well known for its use in mobile devices. For example, it forms the basis of the BlackBerry 10 operating system, as well as the BlackBerry tablet operating system. But really, that's only the tip of the iceberg of QNX usage. Especially these days, it's far more prominent in automotive. It holds more than 50% of the market share of infotainment systems in automotive, and it's slowly being integrated in various self-driving car platforms. For example, BlackBerry announced a partnership with Delphi Automotive to make QNX the basis of its autonomous driving platform. Another interesting application is the fact that QNX forms the basis of the Cisco iOS XR operating system, which is used in Cisco's carrier-grade routers. So that's obviously an interesting target as well to look at. And outside of that, you find it in a lot of critical embedded systems, ranging from industrial control systems, such as the Westinghouse nuclear power plants, to Caterpillar surface mining control, turbine controllers, HVAC machines, defense applications like military radios or anti-tank guidance systems, medical systems, railway safety, you name it. So there's plenty of reasons to be interested in taking a look at QNX. So some of you who've seen my presentation at not last CCC, but the CCC before that might remember that I talked a little bit about QNX there as well, in the talk titled Wheel of Fortune, where I focused on PRNG issues in various kinds of embedded systems. Now, in this talk, there will be a lot of new content. For example, we'll talk about the new QNX 7 user space and kernel space PRNGs, and we'll focus on the previously undiscussed exploit mitigations for QNX 6 and 7. So let's start off with the operating system and security architecture of QNX. Now, QNX has a security history that's relatively sparse. So there has been some research into QNX, but that was mostly by proxy from the BlackBerry mobile research community, which has died off in recent years for obvious reasons. In 2016, there was a very interesting talk by Alex Plaskett on QNX, IPC, PPS, and kernel call security, which is definitely worth checking out. And there have been various individual vulnerabilities discovered over the years. And as you can see on the pie chart on the right, what's interesting is that most of these vulnerabilities have been either SetUID logic bugs or memory corruption vulnerabilities. And that's interesting to keep in mind. Another point of interest is the fact that as part of the WikiLeaks Vault 7 releases, it was noted that the CIA's embedded development branch had shown an interest in QNX exploitation as part of their focus on vehicle exploitation. They noted as of 2014 that no work had been done, but that might have been changed in the meanwhile. Obviously, we don't know. What was interesting from taking a look at the QNX security history is that there had been no prior work on exploit mitigations or PRNGs at all. This had not been discussed before, and the internals hadn't been really covered well. So that's what this talk is going to focus on. So when starting reverse engineering QNX, there's a couple of sources to start. The obvious sources are the QNX developer support pages, obviously, which document some functionality, but not very in-depth. Then there's the QNX community portal, which has a lot of sources for board support packages, networking stacks, the operating system wiki, which has some information on the scheduler and stuff like that. But most of this stuff does not cover the interesting stuff, or at least what was the interesting stuff to me, which are the QNX features which are available on version 6.4 and higher, such as the mitigations or the PRNGs. So we obtained the software development package, which includes the RTOS itself, system binaries, and the Momenting tool suite. And luckily, all the binaries in this package come with debug symbols available for my QNX members, and that greatly eases the reverse engineering effort. You can just load the microkernel itself into IDA with the symbols and take the manual reverse engineering route, which is what I did. So let's start with the QNX boot process. As you can see on the slide, the QNX boot process starts with the initial program loader. After hardware initialization, it copies the image file system to RAM. And after that, a startup program, for example, for a BIOS on machines which have that, configures the system, like the interrupt controllers and stuff like that, and hands over control to the actual microkernel itself, called proc_nto, which sets up the kernel, runs a build file, which is basically a boot script for drivers and operating system components, and then the full boot process has been initialized. QNX firmware always comes in a standard format. There are various kinds of QNX operating system packages oriented towards different industry verticals. So you have QNX car, you have QNX safety, QNX medical, but all of these use the same microkernel and the same core service binaries. So regardless of these differences, the only differences are in some user-land applications. The QNX images that you might find in firmware come in three flavors, either an operating system image, which is the IFS type, a flash file system image, which is the EFS type, or the embedded transaction file system type, which is the ETFS. And you can see an example of an IFS layout on the top of the slide. These images can be combined into a single image, which is how you often encounter them, for example, on a NAND flash chip. And then you can see them being combined in a layout that always looks somewhat like on the bottom right of the slide. Unpacking them is very easy because QNX provides utilities for that. You have the dump IFS and dump EFS utilities. So if you have the QNX SDP, you can use these utilities to unpack QNX firmware images, as you can see on the slide. That's relatively trivial and straightforward. So let's take a little look at the operating system architecture. QNX is a true microkernel architecture, so that means that only the bare minimum of services actually lives in kernel space. The task scheduler, interrupt handling, that kind of stuff. Anything that does not belong to this set of minimal functionality lives in user space, and that includes operating system tasks, that includes device drivers, that includes protocol stacks, and all the things that in a monolithic operating system you might find within the kernel itself. There are many reasons for this. One of the main reasons is for reliability, because if there's like a vulnerability or even a non-exploitable bug in one of these functions, then unlike in a monolithic system, it won't bring down the entire system with it. So that makes for a very reliable modular operating system. Now, obviously, all of these components will have to communicate to each other. And they do this by means of inter-process communication via message passing. And the model here, as you can see on the slide, is relatively simple. So you have a client-server model. You have one application that acts as a client, opens a channel by using system calls provided by the microkernel to another server application, which also lives in user space and which receives these messages being passed to it by the microkernel. So that means it spends relatively little time within the microkernel itself and most of the time in user space. These messages will be service specific, and if you develop like a service for QNX or some component, then you can define your own communication here. QNX supports a very minimal set of native system calls. It supports threading calls, message passing, signals, clocks, interrupt handling, all that kind of stuff. But if you compare it, for example, to Linux, you'll see that QNX always has like under 90 system calls, whereas Linux will have over 300. So it's a very lean microkernel. The prototypes for these system calls can be found in the neutrino.h file in the SDP. But obviously, it's a POSIX-compliant operating system, so it will have to implement this functionality somehow. And how it does this is by implementing them as stubs in libc. So in libc, you will find all the functionality you come to expect of a POSIX system, and they will hand it off by means of message passing to some kind of service in user space, which actually implements the functionality. So it doesn't really exist in the kernel. And what's interesting from a security point of view here is that the kernel attack surface is relatively small, but the IPC surface, as a result, attack surface, is relatively large. So that's an interesting part to focus on if you do security research on QNX. A little bit about how the system calls work. Native system calls are invoked with the usual instructions, the sysenter instructions, interrupt 28, software interrupts, all that kind of stuff. The system call number is stored in EEX on x86, in register 12 on ARM, and register 0 on PowerPC. The listings for this stub is found in kernel_calls.h. The system call entry point resides in the kernel entry or the kernel sysenter function, which basically saves the registers, switches to the kernel stack, gets an active kernel thread that is currently active, waits until we are on the right CPU, and then acquires the kernel. And the system call number is then used as an index into the kernel call table, as you can see on the right of the slide, which is dispatched. So a little bit about the memory layout on QNX. It's relatively similar to most Unix-like operating systems. You have a clear kernel space and user space separation, which is not always the case in embedded systems. Only the microkernel actually runs in this kernel space part. User space has separation of sensitive code from regular applications by using virtual private memory using a memory management unit. Obviously, this is only present if a memory management unit is actually present on the system. And this allows for Unix-like process access controls to separate processes from each other. User management on QNX also looks like most Unix-like systems. You have the typical user and file permission model. You have all the etc passwd, etc group, etc shadow files, the usual utilities that come with it. But what's interesting to look at are the QNX hashes. QNX 6 has support by default for the SHA-2 format for hashing, but it also has backwards compatibility support for MD5, DES script, and QNX script, which is interesting if you look at the top right of the slide, was cracked already in 2000 because it's not a hashing algorithm, it's fully invertible. If you have a hash, you can just run it through an application, and you get the plain text right back without any kind of information loss. This is the reason why this is still present, when you still encounter a lot of QNX firmware images, for example, with Descript hashed passwords, is for backwards compatibility reasons. So there are a lot of systems out there that will still have these insecure hashing. And you need to consider that a cracked root or maintenance password in an embedded system can have a very high shelf life because people don't always do firmware updates, or the systems might not even be updatable in a very regular way. So the potential consequences of this are fairly serious. Luckily, as of QNX 7 or patched 6.6 versions, they now by default have PBKDF2 with either SHA-256 or SHA-512, so that's at least an improvement. The QNX process manager is combined with the microkernel in the proc NTO executable. It runs as a root process with PID1. It's always the first process that's actually started up. And it invokes the microkernel in the same way as other processes. So even though it's bundled with the microkernel, it doesn't have like a dedicated special interface for interacting with it. What it does have, and that makes it an interesting target, is it has the NTO-PF ring 0 flag, which allows it to invoke a dedicated system call called ring 0, which basically allows you to pass a pointer, and then you can execute arbitrary code at that location. So that's meant for the process manager only, but if you compromise the process manager, then you can also use this. So there's support for the usual POSIX stuff. You expect spawn, fork, exec system calls. It uses the ELF format, so that's very familiar as well. And what's interesting is that if the file system resides on a block-oriented device, code and data are loaded into main memory. But if the file system is memory mapped, such as on like a flash device, then code is executed in place. So multiple instances of the same process will share code memory here, which has some interesting implications. QNX has process abilities, which is similar to Linux capabilities. It allows you to obtain certain capabilities before dropping root privileges. So that means that you can adhere to some principle of least privilege. And QNX basically builds this as rootless execution security. So you can have an application that needs some particular capability but not be full root. These abilities have a domain, being able to set it to root or non-root. A range, you can restrict it to certain values. So for example, if you want to grant a process the capability to spawn a process with a certain set UID, you can restrict the range of the set UIDs. It can be made inheritable, it can be made locked. So there's relatively granular control over this kind of stuff. And you can specify custom abilities as well. Now, there are some limitations to this QNX processability model. It's obviously up to the application developers and system integrators to get this right, and that's not very trivial. You need to really watch out, for example, with the inheritability flag, because the inheritability flag itself is inheritable. Fork, for example, ignores this, but spawn honors this, and that means that depending on if you want a child process to inherit a capability, but maybe not the child process of a child process, you really need to think this through. Some functionality is also uncovered by capabilities. You can't restrict any file system interaction or network interaction functionality with it, so don't try to treat it like a full sandbox. For example, a root process with all capabilities dropped can still chmod or chown. Some capabilities don't have ranges, like the process manager AAD spawn capability. You can spawn whatever you want. There's no restrictions like on file path or something like that. Various capabilities can also be used to elevate privileges to root, even if you are not root. So that means that a low-privileged process with certain capabilities can use that to elevate themselves. And in some cases, it's very obvious. Like if you have the spawn set UID capability without a range, then obviously you can use this. But in some other cases, it might be obvious to security people, but not to embedded system integrators, like the process manager aid interrupt capability. So it's not a true sandbox. To show how this is the case, you can trivially break rootless execution under conditions where you have I/O capabilities and interrupt capabilities, which allows you to attach an interrupt handler. And to most people here, it will be probably obvious that, yeah, obviously, if I can attach an interrupt handler, I can run code in kernel space, and then it's over. But this is a thing that, if you look at a lot of QNX systems, that doesn't exactly fit within the security model that people have in mind when they hand out this capability. So this is a thing to really keep in mind there. Another very interesting part of QNX is the native networking called Qnet. So we previously talked about the IPC message passing interface. What Qnet allows you to do is act like a transparent layer over any kind of packet driver. So regardless of whether it's an Ethernet packet driver, a serial driver, any kind of interconnect, you can put Qnet on top of it, and then you have transparent distributed computing. And this can be used, for example, to pass messages around with the IPC as well. As you can see on the right of the slide, you can have them communicate to a single microkernel, but you can also have them communicate across a network of microkernels. And this is really interesting for all kinds of applications. For example, it's used for intermodule communication in industrial control systems. So let's say you have like one QNX machine that's on one part of the factory floor, and you have another machine that's all the way on the other side, and they're connected by, I don't know, like some serial cable or maybe an Ethernet connection or cellular or whatever. Then they can communicate with each other over IPC, over Qnet. You might also encounter it for being used in sharing cellular modems or Bluetooth transceivers among electronic control units and automotive. And a very interesting use case is the fact that large routers, which have multiple interface cards, each of which run their own instance of the QNX microkernel, use it for their IPC as well. Cisco's iOS XR, for example, uses Qnet in this fashion. Now, the way Qnet works is that if you log in, as you can see here, and Qnet driver is enabled, and it's enabled on the other nodes as well, then it will slowly start to populate the network directory. And you can see all the nodes that are active on Qnet right there, and you can query them for some information about, what kind of processor is it running, and what kind of processor are active, and that kind of stuff. Now, Qnet was designed to be used among trusted nodes. So that was the design philosophy. Like, it's going to be used like in an air-gapped network, maybe among, I don't know, something like a CAN bus or something like that. There's no untrusted nodes that might be compromised and in turn use Qnet to pivot. But that's not the reality anymore these days. A lot of systems that have been designed to be integrated only among trusted nodes have had nodes added, which in turn might be exposed to the wider world. For example, let's say in automotive, you have several trusted nodes, and certainly a telematics unit gets added, which is then exposed over cellular or Wi-Fi or something like that. This is a problem with Qnet because there is no authentication. It's an unauthenticated protocol. It simply passes a user ID as part of the Qnet packet to the remote machine. And the remote machine then takes a look and says, what's your user ID? And he says, I believe you, and allows you to execute anything under that user ID. And this is worrying because you can also execute commands remotely over Qnet. As you can see, for example, on the slide there, I do a uname on the local machine, and I can use Qnet to execute it remotely on another machine. And I can do this with whatever I want under the user ID I'm currently on my own local machine. And this means that the compromise of a single QNX node or the underlying network link allows me to compromise all the Qnet nodes that are on there. And I have access to all of them at the UID level I already possess. maybe even more because Qnet packet integrity and authentication is completely absent. So there's nothing really stopping me from forging a UID and using it as part of a privilege escalation scenario. Now, there is a little bit of a security feature that might be used to mitigate the worst impact of this, which is the map any and map root options, which are kind of similar to BSD's NFS. Here you can map an incoming UID to a lower privileged UID. So that means that regardless of whatever UID is specified in the Qnet packet, the Qnet packet is treated as if it were that UID you map it to. Let me briefly grab a bit of water here. So this is not the worst because, like, regardless of these map any and map root capabilities, I found out that Qnet has an escalation of privilege vulnerability. So read permissions of operations over Qnet are not actually properly resolved by the resource manager. This allows for an arbitrary remote read access. So regardless of my user ID, regardless of the permission settings on files and processes and all that stuff, I can arbitrarily read any file on any Qnet machine across the Qnet interlink or locally. So you can see here, for example, I'm on a local machine, I'm a low privileged user, I have the shadow file, don't have read access to it. But if I execute this command on a remote Qnet node and then allow it to use Qnet again to read that file, then the remote node can read it and I can read my own shadow file. So, you know, this completely breaks any kind of security model you would want. A patch for this is available. So, you know, in some systems that are fully patched, you might be able to use map any and map root, but really the Qnet security model is fundamentally broken. Now, I've talked to BlackBerry and they said they are working on improving this. I don't know if that means like a complete redesign of Qnet or something like that, but this is really something to watch out for if you're responsible for either product security or doing an assessment of a QNX-based system. A little bit about QNX debugging. It has a relatively fully featured debugging environment. The QNX Momentix IDE integrates GDB debugger capabilities for various kinds of architectures. You have the pdebug utility, which is a process-level debugging utility that you can talk to over either serial or TCP/IP. There is the Qcon service, which offers remote IDE connectivity and is basically a wrapper around pdebug, starting by default on port 8000. This is definitely something you want to check that people don't leave in production systems because there is no authentication. And some of the functionality that's integrated into Qcon allows you to upload and download arbitrary files and run anything as root right away. So if people leave the debugger on there, then you know they're fucked. There is actually a Metasploit module for this to make it much easier. There is a dumper utility. If this is enabled on a system that you're currently debugging, it ensures that after every crash, a core dump will be available in the var/dumps directory. You can also directly dump a running process with a PID flag. And this, I found this is quite nice for integration into fuzzing utilities. There is a kernel debugger, which you can talk to over serial. This needs to be included with the IFS. This is not the case by default. Depending on the architecture you're compiling it for, you might have to build it completely from source, and the source is not directly available. So this is kind of a pain in the ass. In order to deploy it, you will also need a debuggable microkernel. So you will need basically to have the full SDP to try and toy around with this, or yeah, else it's not going to be nice. For kernel dump debugging, they have like a special format in QNX. That basically specifies that once a kernel crash happens, you get the signal code and fault IDs, which are defined in various C header files as part of the SDP. It specifies the kernel code and data location at the time of the crash, the kernel state, gives you the kernel stack base, the process and thread IDs active on a particular CPU at that time, the process and thread flags, the instruction where the actual issue occurred, the register values at the time of the crash, and the stack content. So it's relatively verbose, and that's very nice when debugging kernel crashes. And that brings us to the pseudo-random number generators on QNX. So first of all, why take a look at PRNGs? I mean, it's kind of obvious, but still. They're the foundation of the wider cryptographic ecosystem. In many cases, and to many developers and system integrators, just use def random, you know, and your good is received wisdom, and that should be the case. Providing secure randomness, at least in my opinion, is an operating system service. This is not something that people without a security background should have to go and implement and check themselves. The operating system should provide strong, secure randomness as part of its API. The strength of exploit mitigations in many cases, or should depend as well on the strength of the PRNGs. Think of things like stack canaries, think of things like ASLR, they all should draw upon the operating system's secure random number generation functionality. So if I don't find strong PRNGs, that also makes exploit development a lot easier in practice. QNX has a couple of PRNGs. It has a user space PRNG, like most Unix-like models, is accessible through dev random. It's handled by a user space service called random, which is running as root in user space. It's started after boot by a startup script, so that's kind of interesting, because if you have services that might be started before the random service, then you get kind of a race here. It's non-blocking too, because you don't want this to be blocking for various reasons. There is no kernel space PRNG in QNX 6, but there is one in QNX 7 after the findings of my research were reported to BlackBerry. It's implemented in a microkernel as a function named random value, and I'll discuss it a little bit later on. And it cannot be accessed directly in user space, so it's only for kernel space secure random functionality. Now, the QNX 6 user space PRNG was covered in depth in my talk at 33C3, so I won't delve into all the details here, but I'll give a brief recap. It's based on Yarrow by Bruce Schneier et al., but it's based on an older Yarrow version, not actually the reference design. So it's an older version that was found to be insufficiently secure, and they basically copied it, didn't take the reference Yarrow version. They added some very sketchy cryptographic design decisions of themselves on top. On top of that, a bigger problem was the fact that it had very low quality boot time entropy. So as you can see on the top right of the slide, when the PRNG starts up, it collects boot time entropy from a couple of sources. So it takes clock time, which is basically the system time, clock cycles, which is a free running clock cycle counter. It takes a list of the currently active process IDs, which basically is always the same when starting up, especially in a very limited embedded system, and the device names, which is as good as static. So the entropy quality of this is quite terrible, and when evaluating it, we found it to be very, very predictable, but you should probably check out the 33C3 talk for the details on that. On top of that, it had broken reseed control, so that meant that in practice, none of the runtime entropy that would otherwise could have saved it was actually fed back into the PRNG state. So it was collecting runtime entropy and storing it in a pool, but then never mixing it back into the PRNG state again. So, it wasn't doing anything. And then you were just left with this terrible boot time entropy. Now, after this assessment I did, the feedback was integrated back into QNX 6 patches and the new QNX 7 design. They now use the Heimdall-Fortuna implementation, which is an improvement. They have new entropy sources, they have new reseed control mechanisms. The overall quality seems much better than QNX 6, but there still is some potential for weaknesses depending on system integration conditions. And this is kind of an important point here, because if you're developing an embedded operating system, then you can't really know all the kind of systems you're going to be deployed on. So some might have entropy sources that are high quality, some might even have a true random number generator, all that kind of stuff. Some other ones might, not have any suitable source or one that you can integrate into the operating system secure random number generator by default. So it's always important to look at system integration conditions. Now this is what the new PRNG looks like after reverse engineering. So it's Fortuna, and the sources in green are the new sources that were added as of QNX 7. So now they have a seed file, which basically allows you, when the PRNG starts up, to specify a file with the right permissions, of course, and read from it and feed that into the PRNG state. And then when the system shuts down, it takes some PRNG output, writes it to the file for the next boot time. And the reason why this was included is to prevent these low boot time entropy conditions. When an embedded system often starts up, there is very little activity going on, and whatever activity is going on is very predictable. So because of that, usually boot time conditions for entropy are the worst in embedded PRNGs, but it's also usually the time when a lot of security critical elements are generated. Think of, cryptographic keys, maybe nonces as part of some challenge response, that kind of stuff. So that's why they integrated the seed file source for the new PRNG. The other source they allowed for now is a user-supplied source. Basically, they made the dev random interface writable. Unfortunately, by default, it's world writable. That's not supposed to be that much of an issue with Fortuna, but that really depends on the selection of other entropy sources. If this is the only entropy source, then it's kind of a problem. The user-supplied source basically means that system integrators can write an entropy gathering daemon to do whatever they want, interface with whatever kind of PRNG driver or whatever they want, and supply their own entropy. Finally, there's also a new reseed source, which unfortunately, despite good intentions, is not that strong because it consists of getPID, which is always static because it's the process ID of the random service, which is the PRNG, so that's not really random. The time of day is also not like a high-quality entropy source, and the UID is static as well. The only mitigating factor here is that it takes RC4 random as a function and feeds it in there. And, of course, RC4 shouldn't be the first choice, but it takes entropy out of the PRNG itself, feeds it through RC4, and then feeds it back in again. And for the rest, the entropy sources are more or less the same. So if you encounter a QNX firmware image, look at the system integration conditions and what entropy sources they selected for their particular system. Now, they also introduced a kernel PRNG after our assessment, and this is mainly used for ASLR and stack canaries currently, and a little bit of other functionality, and maybe down the line some other security features that are probably part of their roadmap. It looks like this. So the way it works is you have a PRNG input block, and that collects entropy. Like when the function is called, it's implemented as a random value function. It collects entropy from a couple of sources. So you have clock cycles, which is the current clock cycle counter, the current PID that is currently active in user space, the current kernel time in nanoseconds. It takes the currently active thread and the currently active CPU, the wake-up timer, the kernel exit count, a salt value, and a random seed value, and it all concatenates these into a PRNG input block, and then pulls the PRNG input block through SHA-256, and then chops it up into different blocks, and the first of those blocks is kept secret and used as the next salt for the next time this thing is called. And then the second block is output as a random 32-bit value. And the next time you call the function, it just increments the counter within the PRNG state, outputs a block until it has exhausted the PRNG state, and then does the whole thing over and over again. A word of note, what's interesting is that they now have this random seed value, and this can be set from user space. So they added a whole additional system call for this called sys as random, and you can call this, and this allows you to set a 64-bit random value that is fed to the PRNG every time that it's called. This requires the as random capability though, so this is an additional thing. And that brings us to the exploit mitigations of QNX. So why take a look at exploit mitigations? Well, the mitigations that we're used to in the general purpose world, Windows, Linux, BSD, they didn't come falling from the sky. So there's a long history of weaknesses, subsequent bypasses, and improvement in general purpose that we're not used to in many embedded systems. So when we do encounter mitigations in embedded operating systems, which you almost never do, they often tend to be a homebrew or to be in the very early stages of implementation, especially if the architectural lineage, like is the case with QNX, is not the same as Windows, Linux, or BSD. So they can directly port whatever improvements have been drafted there. You can see that for Windows it took quite a few years to get to the very strong point where it is now, and we're definitely nowhere near that point in embedded systems. QNX has support for the following exploit mitigations. So it has support for data execution prevention, address space layout randomization, stack canaries, and relocation read-only. These are not enabled by default, however. So unless system integrators explicitly enable support for all these mitigations, it will still be exploiting like it's the 90s. So definitely take a look at that. There is still no support, and as far as I know, there is also no roadmap for integrating things like vtable protection, control flow integrity, or kernel date and code isolation. So don't expect any of that. No. So QNX DEP relies on hardware-based DEP support. So for example, the NX or XIN bit. It has support for that feature on x86 and x64 on ARM, every version after 6 and more. It doesn't have support for this feature on MIPS, is interesting to note, even though MIPS after, I believe, MIPS 32 after release 3 has support for a feature like that. And for PowerPC it varies, but you know, that's PowerPC. The problem with the QNX DEP implementation is that the defaults are insecure. So by default, the stack is always left executable, even if the NX bit is present, even if you have a CPU that support or a memory management unit that supports this kind of feature, then the stack is still executable, even if the heap is not. What's worse is that if you compile and link all your programs with the right flags, you know, the GNU stack elf header, setting the right permissions, this is completely ignored by the program loader. So it doesn't matter what you specify, it says, I don't care, stack is executable. You can make it non-executable by specifying a flag, the M X flag, in the microkernel startup options to make the stack non-executable. But the problem is that this is a system-wide setting and there is no opt-out for it. So any applications which might need an executable stack for whatever reason, and usually that's legacy applications generating, I don't know, trampoline code on the stack or something like that, then these things can no longer run. And legacy applications are a big thing in many embedded systems, so people will not enable it. They should have had at least an opt-out model here. Now, this has not been addressed or fixed, so this is an issue that is still present on QNX 6 and even QNX 7. So if you take a look at the QNX firmware image, take a look at the microkernel startup flags, and you might just find that these have not been specified and you won't really have to bother with anything else because you have an executable stack. QNX ASLR is enabled by, again, starting the microkernel with a dedicated flag. Child processes inherit their parents' ASLR settings. And these can be enabled or disabled on a per process basis. So you have a very granular opt-out model there. QNX ASLR randomizes objects at the base address level. And it randomizes almost all memory objects except for the kernel code image, as you can see here on the right. How terrible that is depends on your opinion of KASLR, but it's relatively good in its support for randomization of most memory objects. Unfortunately, position-independent executables are disabled by default in the toolchain, and none of the system binaries that you encounter in the default installs of QNX will have PI enabled. So that means that the main program image will not have randomized code, so that makes wrapping a lot easier too. In order to learn how QNX ASLR works under the hood, I reverse engineered the memory manager. And the way it basically works is you have user space ASLR and you have all these different memory objects, and it all comes down to the mmap call in the microkernel. Now, randomization is done by the two functions in blue, regardless of whether it's user space or kernel space ASLR, and that's stack randomize and map find virtual address. And both use the same RNG, I should say, which I'll discuss shortly. Now, the first of these functions is mapfindVA, which, among other things, randomizes the virtual addresses returned by the mmap call. And the way the randomization works is by subtracting or adding a random value to or from the found virtual address. And this is done, as you can see on the right of the slide, by taking the lower 32 bits from the random number generator result, bitwise left shifting them by 12, and then extracting the lower 24 bits and applying it to the found virtual address. The problem of this bit mask is that it results in at most 12 bits of entropy as an upper bound for any randomization of addresses in QNX. And this is worse in practice, as we'll see. The second function is stack randomize, which randomizes stack start addresses. So it subtracts a random value from the original stack pointer just when a stack for a thread or the main thread or spawn thread is allocated. And it's very similar to the previous function. It takes the lower 32 bits of the random number generator result, bitwise left shift them by 4, and then at most extracts the lower 11 bits. Can be less, depends on the size of the stack that's being allocated. But again, the problem here is that this contributes at most 7 bits of entropy to stack randomization, which is worse in practice. It's a little bit mitigated by the fact that it is combined with the results of the previous mapfindVA function, but you know that won't matter a lot. The real problem with QNX 6's ASLR implementation is that it has a weak random number generator. The upper bounds that we just saw, the 12 and 7 bits, are actually optimistic. QNX 6 ASLR uses a weak random number generator because it only relies, as some of you will already have seen, on the clock cycles call. And what's the clock cycle system call? Well, it's basically a call that receives a 64-bit free-running cycle counter. Now, this is implemented differently depending on the architecture you have. So on x86, it will be the RDTSC instruction. On ARM, it will result from some emulation within the microkernel itself, the counter register on MIPS, all that kind of stuff. Now, the problem is that we evaluated the actual entropy here, and we measured various kinds of processes across different kind of boot sessions, and then harvested the resulting randomized memory object addresses. Then we used the NIST entropy source testing tool to obtain min entropy estimates for all these different measurements. And just as an aside, 256 bits of uniformly random data should correspond to 256 bits of min entropy. Now we found the average min entropy of an ASLR randomized address on a 32-bit system on QNX to be 4.47 bits. And this is very weak, especially when you compare it to mainline Linux ASLR on 32-bit or PAX ASLR. As you can see on the right of the slide, here on 32-bit systems, you have 27 bits, 23 bits, maybe at worst something like 8 or 6 bits in the on the edge cases, but nowhere near 4.47 bits. And an interesting thing to note was that actually the worst scoring memory objects here were things like shared libraries, which had 3 bits of entropy. So, you know. Why is this an issue? Well, this is an issue because of the potential, for example, for brute forcing. So QNX, like a lot of systems, has memory layout inheritance. So when you have a parent process and it forks to create a child process, that means that it will copy the memory layout of the parent. So it will also, because ASLR is applied before that, it will also copy the ASLR layout. Now, if you have an auto restarting functionality, let's say you have a networking daemon and you use a child process to handle incoming connections, and then when the connection dies, you know the child is respawned. That means that an attacker can try to guess an address as part of the attack. The child dies, it respawns with the same ASLR layout, and then you can try this iteratively until you hit your particular payload. Does this work in practice? Yes, this works in practice, and it works remotely. So, as you can see on the left of the slide, you have a vulnerable network service running on port lead, and on the right, you have an exploit for it, which in 23 seconds pops a root shell over, despite ASLR being enabled. So this is kind of, well, almost to say useless. Now, outside of the quality of the ASLR randomization, we also found a number of issues with information leaks. Just to discuss 2 of them, but there are many, many more if you look at that. The first we found was the process file system information leak. So on QNX, like on many Unix-like systems, you have a process file system, which has a bunch of pseudo files for every running process. And they contain some information if you want information about the currently running processes. You can interact with them using the devctl API, and there you can query information, for example, like the process ID, the memory layout, and even very granular information like a full stack backtrace, the current program state, the registers, all that kind of stuff. And what's interesting, if you can look at the top of the slide, is that this interface by default is world readable. So, you know, regardless of ASLR being enabled, a low-privileged user can read the memory contents of any process that is there. And what this looks like in practice by running a small script to interact with it is, you can see over there. you're a low-privileged user, you interact with the microkernel itself, and then dump the program state and the memory layout mapping despite ASLR being disabled. And what's really interesting is that QNX actually provides a utility called PIDN, which allows you to do exactly this. So even if you can't, compile code on a particular system, run your own thing, a utility that does this for you might be included already with QNX, and that is very nice. The second info leak we found resides in the Aldi debug functionality. So Aldi debug is an environment variable where you can specify some information and then the application is started with debugging information. Now, it has an interesting option called all, and all will allow you to dump a lot of information from the program loader. So as you can see, it will dump information like the loaded libraries and at what address it's loaded and all that kind of stuff. The interesting thing is that on this functionality like this is present on Linux and BSD like that, but it at least has privilege checking. But here, this functionality has no privilege checking. So even if I'm a low privilege user and I execute a setuid application, then it will just give me all the information about the application there, regardless of privilege barriers. And that presents with a nice other information leak as well. Now, QNX 7 has some changes to the ASLR as a result of what we reported, and ASLR is still disabled by default, and there's no KASLR, but luckily they now use the kernel PRNG we previously discussed to do the randomization, so that's definitely a step in the right direction. Unfortunately, despite using this new random number generator and having a 64-bit address space, these low theoretical upper bounds remain. So they didn't remove the bit masking that's applied to the applications. So that means there is still an upper bound of 7 bits for stack randomization and 12 for, most other memory regions. An interesting thing on the side of that is that it always will load code memory in the lower 32 bits of the address space, even on a 64-bit operating system. I communicated this back with BlackBerry, and they said they were working on changing this, but in the current versions of QNX 7, this is all still present. They also fixed the Aldi debug vulnerability, but unfortunately the process file system vulnerability was not completely fixed. So you can see that they restricted the PIDN utility for not dumping the information that you shouldn't be able to dump, but if you write, an application to directly interact with the process file system yourself, you can still all get it on QNX 7. So this is an info leak that's locally still there on QNX 7. The other mitigation on QNX are stack canaries. QNX uses GCC stack smashing protector model. The compiler-side implementation is what we're used to for GCC, and it's kind of okay. The problem is that the operating system side implementations are custom. So the user space master canary is generated at program startup when libc is loaded. But usually libSSP has guard setup function, which does the generation of the master canary. Now QNX doesn't use this. It uses a custom init cookies function, and that's where the trouble starts. Again, it has a weak random number generator. It draws entropy from 3 sources, only two of which are only relevant if ASLR is enabled. As you can see on the bottom of the slide, again, all the randomness is based on clock cycles. So it takes, again, a read from clock cycles and then XORs in the address of a local stack variable and the address of the function itself. And these last 2 things will obviously only be randomized if ASLR is enabled, but even if it is, it relies on clock cycles. So again, we evaluated the canary min entropy across 3 configurations, without ASLR, with ASLR but without position-independent executables, with ASLR and with position-independent executables, and found that the average min entropy of a canary in a 32-bit system was 7.79 bits. And ASLR had no notable influence here at all. And this is less than ideal, because if they had used a secure random number generator, they should have had 24 bits of min entropy if they had like a Terminator-style null byte in the middle against string copy functionality, but they don't. In kernel space, the problems are even worse. Because the microkernel is neither loaded nor linked against libc, obviously, master canary generation cannot be done by this init cookies function. The problem is that instead of handling this by writing a function that should have been a replacement here, QNX actually forgot to implement a master canary generation routine for the kernel at all. So kernel space canaries are used everywhere, but they're never actually generated, and they are always 0. So that's a very nice kind of canary. They made some changes after we said this is probably not the best idea to go about this. They're now enabled by default. They on QNX 7 they generate 64-bit canaries. For user space, QNX mixes in the ELF auxiliary vector value 80 random with the init cookie stuff they already did. And this basically, what the ELF auxiliary vector value is, it transfers kernel information to the user process upon startup. And the information it transfers is basically a 64-bit value generated from the kernel PRNG. So that's a good way to go about it. For kernel space canaries, QNX simply concatenates to 32-bit kernel PRNG values during very early boot, so before most of the canaries are relevant. And the final mitigation that we're going to discuss is relocation read-only, RELRO. What it basically is dynamically linked binaries will use relocation to do runtime lookup of symbols residing in shared libraries. So here, as you can see on the picture on the right, you'll have a function, it makes a call. And in the PLT, you'll have a jump to the function that gets dereferenced at the global offset table. Relocation data of this kind is a popular target for overriding to hijack control flow. Because if you overwrite an entry in the global offset table, here you can hijack control flow whenever that function gets called. In order to protect against this, you have the RELRO mitigation. And RELRO basically reorders ELF sections so that all the internal data sections, like the global offset table, the destructor section, all that kind of stuff, precedes the program data, which is like the data and the BSS sections and stuff like that. The relocation data is then made read-only by being covered by a GNU RELRO segment after relocation is done. The problem is that most applications will have lazy binding. So that means that the resolving of these symbols is only done the moment they are hit. So it's done dynamically. That means that the PLT got is still left writable during runtime, because if you make it read-only, it cannot be resolved during runtime. Now, in order to address this, you have the full RELRO mitigation, which disables lazy binding with a flag, and then the PLT got is also read-only right after startup, at the cost of having a little bit slower startup times. The problem is that even though they implemented it, they took it from GCC and made it compatible, is that they had a broken implementation. So on the left, you can see the implementation of RELRO on Debian. And there you have like the GNU RELRO segment, basically covering all of the internal data sections, which includes the GOT. On the right, you have QNX 6.6, where you have GNU RELRO, which covers internal data sections, but not the global offset table. And the reason why this is the case is because they forgot to do the reordering to make the internal data sections precede the program data sections. And then you have like the GOT, which is the most important thing to actually protect with RELRO, being left writable. So what does this look like? Here you can see on Debian, an application linked and compiled with RELRO protection. You try to write to a RELRO protected part of the executable, and then it's segfault. And on the right, you can, even though RELRO has been enabled in this application, you can still exploit it. So you can have, a toolchain set up with all the right linker flags, completely believe that you're in the clear there, and still be exploitable. We also found a very weird local bypass for RELRO. LDDebug has a fully undocumented imposter option, which allows you to disable RELRO without any kind of privilege checks, which is very nice for exploiting setuid binaries. Both of these issues, the section reordering and this weird imposter option, were fixed with patches for QNX 6.6 and in QNX 7. Now that brings us to the final remarks. All of these issues were disclosed to BlackBerry way ahead of this conference. Most issues were fixed in 7.0. Patches for 6.6 are available for some issues. You can see in the table what is available. The problem is that it will take lots of time before all these patches that are available will filter down to the OEMs and the end users. If you have systems that are deeply embedded, that are not automatically updated, then it will take a long time before all of these issues are out of the field. So this might be exploitable for a long time in the wild. Concluding, the mitigations are mostly okay on the toolchain side. There are some weak defaults, some linker mistakes, but because they rely on GCC, it's relatively okay. The problems really reside on the operating system side, and that's mainly because QNX cannot benefit directly from any work that's been done in general purpose operating system security, because they cannot port one-to-one from Linux, BSD, or Windows to QNX, because it has a completely different architecture. And the result is homebrew DIY mitigations, which are not up to the standard you want them to be. What's also really clear is that there has been a lack of prior attention by security researchers. A lot of vulns feel they're from the early 2000s, especially the info leaks and stuff like that. And the embedded random number generator design obviously remains difficult. Entropy issues means that obviously the design burden often results with the system integrators, and that remains a pain in the ass. On a more positive note, at least QNX attempts to keep up with general purpose OS security. As part of a broader research, I looked at 47 operating systems in the embedded space, and they were one of the very, very few operating systems not based on Windows, Linux, or BSD that even had mitigations at all. The response has been very friendly, very forthcoming, very rapid as well. And what's really needed is more attention to embedded operating system security in general. You can expect more QNX stuff as well in the future at OffensiveCon, Black Hat Asia, and Infiltrate. So if you're interested in that kind of stuff, keep an eye out. And that's that. If there's any questions, I'll hear them now.
Questions? Thank you very much, Jos.
All right.